Okay, so FYI, again, if you have any questions, you just raise your hand. I pause the video, ask questions, I call on you, blah, blah, blah. You don't need to be dead silent out there, but you shouldn't be like that guy over there. It's just super ruckusy. Not the step team. I mean like crazy. So we're going to be talking about atomic orbitals again today. We're going to get into a little bit more depth than you had in your regular chemistry class. One of the things some of you relied upon in regular chemistry was this. Does anybody remember what this is called? Aufbau's order, right? Aufbau's order, really useful for regular chemistry kids. You can build up the number of electrons around the nucleus. Look on your periodic table. Where is Aufbau's order on your periodic table? It is not on there, is it? If you've got one from last year, no. But the one we use does not have it on there. So we need to know how Aufbau's order is hidden right in front of us on the periodic table. So what I have here is a periodic table that already has the configurations written on it. Can you see it in kind of tiny handwriting? Right, it's not handwritten, it's typed. But anyway, so it says like 1s1, 2s1, 3s1, 4s1, bless you 1, 6s1, 7s1. Guess what every element in the first period has as its last an S1, and then if you count the number of levels down like Mrs. Hoffman does, you can tell what energy level. Like this is 1, 2, 3, 4, 5, 6. Cesium ends with 6s1. Isn't that true? That was the tightest. Yup. She hates having her voice recorded. That was very Chloe. That was Mrs. Hoffman. And so the periodic table is actually arranged in Aufbau's order. Here's a better periodic table for this conversation. It's in Aufbau's order. It is. If you throw helium right here, you'd have 1s1 and 1s2, 2s1, 2p, 3s, 3p, and it slowly builds. So when I ask her who's on her phone right now, pick an element, please. Give me an element. Big element. Mercury, thank you. Mercury is way down there, right about here, I think. How'd I do? All right. So you have to get all the way there. Mercury is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. The D's are off by 1. That's why it's called Aufbau's order. Not really. But they're always out of order when you hit the d orbitals for the first time, and they continue to be off by 1 the entire rest of the way. So it goes 4s, 3d. 4 levels down, but these are the 3. D10, 4p, 5s, 4d, 5p, 6s, 5d, and that's the 10th one over. However, what happens right there on your periodic table? There's a break, and it jumps down there for a second, so you have to cruise through the 4f's, or what are those, the lanthanides? The lanthanides. We don't ever deal with the lanthanides or the actinides. We also don't deal with any of the exceptions. There are so many exceptions to Aufbau's order. Like, what would you expect copper's configuration to be? You would probably expect it to be 4s2, 3d9 at the end. It's actually an exception that you don't need to know. But I don't like to 100% lie to you all the time. So here's the true configuration that's going to irritate you slightly. Why? I love, that's my best, the best question is why, right? What's going as we go across, we have more and more protons that are pulling on the electrons, and that 4s2 electron gets pulled in to fill out the 3d. That also happens at a couple other weird spots. And again, I'm going to reiterate, do you need to know this for this next couple seconds? No, but it's just interesting. If you go to the next layer, Caesar says he needs to know it. But the rest, you don't need to know that like every single 1, 2, 3, 4. Every element here is an exception. I wouldn't give you one of those because they're not, like I never ask about the F's because like every other element is an exception in the F's. Aufbau's order works really well for the first several rows, and then it starts to fall apart in certain zones. But we now know what falls apart, and we know what really is occurring there and why. The number of protons right here is strong enough to pull one of the s orbitals in, And what happens there is you have like a 4s2 that's full, and those p's, 1, 2, 3, 4, 5, nope, too many. 1, 2, 3, 4, 5, right? 5 orbitals, and we usually go 1, 2, 3, 4. For this element right here, the protons are strong enough to pull this electron out of this space and into this space. So they're all half full instead of one that's full and half full. We don't need to know that. I just like to throw it out there, though, because you probably will still see that in your regular college chem class if you take it. It's not in the AP curriculum, but that doesn't mean it doesn't exist. Yes, ma'am. Yeah, for all the elements in this column, they all cheat and they all take one electron over. Again, we're spending more time on the exceptions than we need to, though. So let's just clear all those exceptions like they never existed. So what you do get for every test, though, is a periodic table. And you know how the periodic table is arranged. You know how off-bow order is hiding right there. If for some reason you can't see it, you can always recreate it, right? You could go 1, 2, 3, 4, 5, 6, S, 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 2, 3, 4, 5, 6, P, 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 3, D, 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 4, F, 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 and you could create it and then draw your own off-bows order. But that sounds horrible, doesn't it? And then you have to get the diagonals just right, and ooh. Now you just kind of need to get used to the way the periodic table is put together. This isn't on purpose. Off-bows order was discovered through mathematical manipulation, and then afterwards we realized the periodic table was already arranged that way. The arrangement of the periodic table is because of how the electrons are distributed. How the electrons are distributed is based off of the math, and the math and that all kind of comes together in a fancy little triangle. Noble gas configurations, also knowing how the periodic table is arranged can be pretty helpful. You said mercury, right? All right, so what element is right here on the last 5p6? Xenon? This part of the periodic table is not on this one, this entire chunk. Xenon. So xenon is the noble gas that comes before this element. We always reference the noble gas that comes before it. By writing down xenon, we've just written down 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. We've just written all of that down without having to write it down. We just put it in brackets, and then we build on the pieces that come after that. So xenon plus these extra energy levels, sublevels, and electrons is now describing good English, is now describing what the configuration would be for mercury. All right, so that's all review. Some of this stuff in the beginning of the actual notes today, we haven't even hit the notes yet, have we? We just reviewed stuff you already knew, hopefully. Or reminded your brain of something you used to know. Some of you was a year ago, some of it was 2 years ago, some of it, I don't know. Electromagnetic radiation. A lot of this knowledge comes from our understanding of photons and how light moves. You know, right now you only get to see a very tiny spectrum of light. You see wavelengths of light that differentiate by such a tiny amount. The difference between purple, red, and green is so tiny. The wavelengths of blue are 400 nanometers. That is 4 times 10 to the minus 7th meters. Red, 750 nanometers, 7.5 times 10 to the minus 9th. What is a nanometer? Nano means 10 to the minus 9th. That's a prefix you actually need to know. Nano, 9. Nano 9. They go together. So we're talking about 0.00000000004 meters. How far is that? Okay. Put your fingers together and smash really hard. It's the space that's not left, right? And then what's the difference between that and red? Nothing. Almost nothing. But we perceive it constantly. Light is flying around the room, hitting clothes, light's being absorbed, light's being emitted, and we constantly see it. We're constantly seeing this slight difference in the wavelength of light. These other things we can't see. There's a huge quantity of light we can't see with our eyes. We can see with our cell phones and with antennas, things that are in the radio frequency. We use microwaves to heat up the bonds between water molecules. Oh, did you take it in there?
Yeah, I took it before.
Okay. Thank you, Victor. Wavelengths and frequency multiply together to equal the speed of light. The speed of light does not change. It is a constant. It is given on your equation sheet. You don't have to memorize this equation, but you need to know how to use it. 3 times 10 to the 8th meters per second. That's pretty fast, almost as fast as my jokes. That was the first one that got a laugh in a while. Photosynthesis. Photosynthesis uses very specific wavelengths of light to convert. What you might notice is that this wavelength of light, where is it? Right? Oh, we're solving for it, moron. This wavelength of light that I've solved for, 660 nanometers, is over here. What color is chlorophyll? Green. That's the color it doesn't absorb. Right? Would that make sense? Yeah, so it's not going to absorb up here in the green range. I know that doesn't look very green. The Promethean board's losing its ability to make the color green. But so what did I do here? I took the frequency. The speed of light is always the same. I solved for the wavelength. It came out like this. Quite often it just automatically gets converted to nanometers. 10 to the minus 7 meters would be in the 600 range for nanometers. When we're done today, I will PDF this and post it out there on the internet. Okay? This is an equation we're not used to. This is a new one. E, change in energy, is equal to Planck's constant times the frequency of the wave. Planck's constant, new to you? It was new to me the first time I saw it. I regularly program constants into my calculator, so I don't have to type them out. I pick the letter that the constant represents. So in my calculator, H is that value. So anytime I say times H, it's multiplying times that value. What's the speed of light? 2.998 times 10 to the 8th. That's C in my calculator. Does that make sense? So you can do that. How do you do that? All right, let's pause for how you do. That was one of the most important things you're going to learn in life right there. Okay. We have sharing calculator tricks over there. Okay. So Planck's constant, Max Planck or Planck, I say Planck, it's actually Planck. Max Planck is one of these famous scientists at the same time as Einstein. He's de Broglie, Marie Curie, working right alongside them. He's not quite as flashy and glitzy as some of the others as far as his public persona. But he relates the energy of associated with wavelength. And he figures out the relationship between energy and wavelength by putting energy into things and then measuring the wavelengths of light given off hundreds of times, finds this relationship. So it merely is, if you put in the wavelength of any photon of light, you can calculate the energy that's associated with that transition. We're about to go through a whole lot of math that you don't need to know how to do. But it's going to set up, historically, the background for some of the other stuff we need to know how to do. So, all of this math you see here, you don't need to know how to do. But let's just talk about, someone at the door? It's like non-stop door interruption day. Hey, I'm all right. Can I pause, Joe? All right. And he's gone. So here we got frequency and wavelength, and I'm solving for the amount of energy per photon. Your textbook spends a lot of time doing this. We don't do this, though. We don't calculate how much energy per photon. But your textbook spends a whole lot of time calculating it, and it's kind of interesting. You could say, okay, if I burn, in this case, if I burn cesium, if I burn a whole gram of cesium, how much energy is converted into various photons, and you could calculate a whole lot of stuff, which is what Planck was doing. But we're not doing that, all right? Clicking on. You could use it to calculate the energy of a bond. Let's say you wanted to break two fluorine atoms apart. That's what this is. You could calculate how much energy it takes to break two fluorine atoms apart, hitting them with different types of electromagnetic radiation, hitting them at different wavelengths, until you break the bond. Somebody's gone through and calculated the strength of every bond. So you have two atoms. Let's call this the Murphy-Elias atom. And it's got this bond energy between the two. You hit this with photons. You okay?
Yeah.
Okay.
It was just like...
Surprising?
Yeah.
You hit this thing with photons, and you're going to energize it. And you're going to energize it until eventually what happens to this bond? It breaks. And so it calculates what each wavelength is that's needed to break the bond. It can vary drastically between one bond and the next bond. We use that all the time in microwaves. Microwaves interact with hydrogen bonds. That's all they interact with. The microwave oven. I don't mean all microwaves. I mean the microwave oven we have at our house moves at the same frequency and wavelength that the hydrogen bond does between the oxygen on one thing and the hydrogen on another. And it excites that bond and causes it to cause lots of friction inside our food. And if you've ever heated up Pop-Tarts, you ever heated up a Pop-Tart in the microwave? No from you, couple yeses. If you have a jelly Pop-Tart, this is almost worth wasting money on a Pop-Tart. If you take a jelly Pop-Tart, like a strawberry one or something, like put that in there and microwave it, the jelly gets like 1,000,000 degrees, but the breading doesn't. The breading has almost no water in it, so there's nothing to excite. The jelly has all of the water in it, so it takes in all of the energy. And then when you take a bite, your mouth is on fire. So that's my warning right there. So don't try this at home. It will literally be 100 degrees, like bubbling on the inside. That's kind of what this is doing too. You calculate the energy associated with different wavelengths to break bonds. De Broglie, another contemporary of these guys, takes this equation. Have you seen that one ever? No? That's sad. Energy equals mass times the speed of light squared. It's a relationship between mass and energy, and he combines it with the Planck equation we were just looking at, and he realizes that this can be applied to electrons moving around the nucleus. Electrons move with a different velocity than the speed of light. That's why this velocity has changed, because electrons are not photons. They're moving around the nucleus at incredibly rapid paces. That's 6 million meters per second, slightly slower than a photon. Planck's constant, the energy of a photon, you can figure out the wavelength that is traveling on. Now we're starting to get to where we come into play. We get to the Bohr model. The Bohr model was really exciting. It had rings of electrons on it, right? That's usually 2 and then 8. And this is what you see for the first time in 8th grade in physical science. We talk about electrons moving between energy levels. Well, that comes out of, first, you put white light on a prism, you get the entire spectrum. You get a rainbow. If you take one of these lights, well, not one of these, but if you take a natural light that has a wide range of colors, you get a rainbow. I saw one the other day. It was pretty. If, however, you take one type of gas, and we actually have I just have the emitters in the back, but I don't have any gas tubes. You run it through a prism, you can actually split it apart into specific wavelengths, and each element has its own wavelength correspondence. Why would one element only give off certain colors and not all the colors? I don't know. What is different about every single element that is pertaining to this chapter? Different electron configurations. I'm going to pretend that's what you said. And the electrons move around the nucleus in different patterns. When they excite these elements, the electrons get excited, meaning they leave the location they're at. They can't go to any of the occupied spaces, so they go out to an empty spot, and then when they get pulled back in by the nucleus, they have to give off energy. We see that energy as light. And depending on how much energy gets put in, also corresponds to how much is given off. Yes? Do they lose energy when they lose it when they come back into the nucleus? As they're shooting away from the nucleus, they've been given energy. They can be given energy in a couple different ways. What we do with our spectrum tubes is we run electricity through them, so we're like super exciting them. There's actually two very different things you can do. I don't know, you can't see that. Let me zoom in on that. Yeah, that's very zoomed. If you just shoot white light through a prism, you get the full range of colors, Roy G. Biv. If you heat up your element with electricity, then you'll get different wavelengths given off that correspond to its energy diagram. If you shoot white light through a chamber that contains just that element, it's going to absorb only at certain wavelengths, but the rest of the white light goes through. So depending on which way you do it, you can shoot the white light through the gas, and it absorbs only at those wavelengths because the energy is going up and being sucked in, and it doesn't give much back off compared to the white light that's going through. So this is called absorption, where it only absorbs at certain spectrum, versus emission, where you're exciting it up to those different levels. You in the back. Why is fire yellow? Well, okay, let's talk about that. Why do you think fire is yellow? The oxygen, and what are the other common things we're burning? What other element is probably the most common in wood and paper that we're burning? Carbon. The combination of those elements is giving off certain colors of light. If we burn it in different combinations, or let's say your teacher throws some magic crystals in there, look at the flame, it's yellow, it's green, it's blue, right? That's because you're getting different wavelengths from those different atoms that are in there. Yes? So the question is about as you put different amounts of energy in, what do you get different wavelengths? Absolutely. We are only seeing the wavelengths we can see. Oh, yeah. There's the whole spectrum, right? If you put a ton of energy in, you might kick an electron up super high, and as it drops down, it just might be out of our visible spectrum. That doesn't mean it's not occurring, and we have machines that can see it. And there's actually different patterns called, hold up, that we're getting to this right now. So there's different patterns. Did you kick it up from the first level and it's coming back to the first level? Is it coming back to the second level? Is it coming back to the third level? Depending on which energy level it's coming back down to, you get different patterns. And they have different names. There's the Lyman series, the Balmer series, the Paschus, I can't say that word. It's got like a C-H-S-E-C-H-E going on. I don't know how to say it. And depending on where it's going back down to, you get different patterns. You got to put a lot of energy in to excite something from the first energy level to the sixth energy level, and then you're going to get a lot back down. Well, you might not see it. It might be outside of our visible spectrum. All right, back to the guy in the back, and then you. I didn't hear a single thing he just said. That would have to be super high energy. I don't know that I agree with that statement. I'm not willing to record that. I don't think so. I mean, you might get up to ultraviolet with this, but usually X-rays are produced through some sort of radioactive decay. We're going to have to talk offline about that. I don't know. I don't know that off the top of my head. Yes? Oh, yeah. You don't need to ask that. All right, so this is one more equation we don't need to use. It's not on the equation sheet. It's just an interesting equation. It's the amount of energy associated with the energy level and the number of protons. Should the number of protons impact the energy associated with the electron as it moves from energy 4 to 3? This is analogous to, but not equivalent to, Morgan is on the planet, she jumps up into the air with a certain amount of energy, and then she falls down with it. We then put her on the moon for being bad. She jumps up with the same amount of energy. Does she go higher? Yeah, because the moon doesn't have as much pull. If you change the nucleus, there's not as much pull on the electrons back down, and this equation accounts for that. The Z value is the number of protons. N is the energy level you're trying to excite it to, or the energy level it's at. And then the energy as it moves around that energy level. Could you, with this equation, calculate a lithium atom electron at the 4th energy level? And then you could calculate it at the 1st energy level. And the difference between the two would be how much energy it gave off. Yeah, your textbook spends some time doing that. We don't. Okay? That energy difference, though, would be correlated to the wavelength given off, and then you could calculate whether or not an X-ray could be given off. All right, you could calculate at energy level 6, energy level 1, what's the difference? And then you could say, okay, E equals h nu, the frequency of wavelength, the frequency of an X-ray is what? Now I know the energy I need. What would be the transition? I need to go from the 1st energy level to the 94th energy level. Uh-oh. All right. Uh-oh, we've got another rogue student coming in. So you guys don't have homework 5A. This question brought to you by Elias. You don't have 5A because 5A is all of this. We don't need to know how to do this. This is all just setting up that same conversation. When we talk about 1s2, 2s2, 2p6, someone's actually done a lot of math in the background. That math we were looking at was actually easier than the math we need to be calculates these shapes. The math that calculates the s and the p and the d orbitals is called the square of the wave function. It's a probability distribution. What the heck is a probability distribution? Yeah. Got it? It's where they're most likely to appear. Is that where they're going to appear? It's a distribution. So we're expecting them to occur within a certain range. And the SPDF model is, we say it's accurate 95% of the times. Really, the distribution of electrons occurs within that range 95% of the times. It's ridiculously difficult to actually map these things out because what are they doing? They're moving. They're constantly influencing each other. You have electrons pushing electrons around. The Heisenberg uncertainty principle comes, arrows backwards. The Heisenberg uncertainty principle comes into effect here. The faster an object's going, the harder it is to know its location. The more you know about its location, the less you know about how fast it's going. And this is truly a problem when you're talking about electrons because they're moving at thousands of meters per second. The second you know where it is, it's not there anymore. So instead of trying to pinpoint exact locations, we then described their area using a wave function. These are samples of some of the graphs produced. We have the 1s, which is a probability distribution. We'd expect the electrons to be closest to the nucleus. On this 2s, the highest probability is a little bit farther out, or we see a probability a little farther out, and then farther and further, and it kind of maps out these shapes we've been talking about. Our textbook also spends a great deal of time going through the 4 variables to calculate these areas. Here are the variables that and you like in the notes I actually said this, didn't I? It says we won't be learning these number combinations. But they have 4 variables, N, L, M sub L, M sub S. What energy level you're on? Are you in an S, P, D, or F sublevel? Angular momentum. These are the different orbitals. And then, what's the magnetic spin? There's 4 variables that all go into a math equation, and then they pop out various shapes. They have values that go into there. We draw them as arrows still. Does that make you happy to hear? We don't try to draw the fancy shapes. I have pictures of the fancy shapes if you want to see them. Actually, that's not the good one. Here's the good one. The S, the simple sphere. The P, the 2 lobes on the X, Y, and Z axis. The D sublevels are in between the axes for a lot of them. And then the F sublevels are just ridiculously confusing. The math problems going on here are way beyond my abilities anymore. Maybe some of the math teachers in the building, I don't know, not this one. Going back, I skipped some stuff. Again, we kind of hit this at the beginning. What is the coefficient relative to? What does that represent? The energy level. The SPDRF represents the sublevel. Then we tend to draw boxes to represent the orbitals, and those superscripts represent the number of electrons. One thing a lot of kids mess up with is when you have to draw a sublevel and describe the electrons, even if, let's say we're doing not the 5F, let's say we're doing D3. The D sublevel has how many orbitals in it? Ooh, 10. Well, 10 is the number of electrons. 10 divided by 2 is 5 orbitals. There's only 3 electrons to place in this one. It is important to note 3 are half full, 2 are empty. That is space where electrons can shift around. That is important space. That impacts bonding. Do you ever wonder why when you were doing bonding in regular chemistry, we said that S's could be 8 valence electron, not S's, sulfur could be 8, 10, or 12. Remember that? We were like, sulfur can do all these weird things. The others all achieve the octet. Sulfur uses d orbitals when it bonds. It shifts electrons into empty space that's not being occupied. When we do bonding next chapter is going to involve sp and d orbitals again. We're going to talk about hybridized bonding between orbitals, not just drawing dots and connecting them. All right. I'm not going to ask you to ever draw, but what's a p orbital look like? Like dumbbells. It's thick on the outside, very thin on the inside. I usually say they look like a peanut shape. They're kind of thin. They got the 2 sides on the outside. They're on the X, Y, and Z axes. They occupy that space. I found this one today. It's got an S on the inside, a second level S, and then the P's slowly building up. It's way better than my drawing ability. Yes. Good luck. Yeah. Why don't the d orbitals exist on the second energy level? That's also a pretty common question I get. There's not much space in here. Where would the third energy level be? If this is the 1s, the 2s, the 2p's, would the third energy level be in here? It would be out another layer, and then we'd have 3p's, and you start having this 2p's back here, this one's over here. Start having gaps appear. So we don't get to the 3D sublevel until the third energy level because there's just not enough physical space around the nucleus for those electrons to fit in. Ground state is our standard configuration where the electrons are pulled in as tight as possible. Excited state would mean it's out of order. Actually, let me do an excited state. Let's do the reverse of that. What element is this? Mind you, it's going to be a trick question. 1s1, 2s2, 2p1. It's only 4 electrons, isn't it? I can't hear you. It's not the worst one. Why is beryllium the worst one? That's okay. He just seems to be anti-beryllium for some reason. I heard, yeah. What's that? No, you don't want to use that periodic table. That's here. Use this one here. Yeah. So that's beryllium, but it's excited beryllium. Do you see where it's excited? It's not 1s2. One of those electrons was excited all the way to the 2p, wasn't it? It wasn't a huge jump. More likely, if you're going to have a jump, it might be like there. 1s1, 2s2, 4p1. It's been excited past a whole lot of layers way out there, and then the nucleus is going to pull it back in, and it's going to release a photon or 2 of light to get back in. We usually only do ground state, though. We usually only do Aufbau's ground state configurations. Everything pulled in as tight as possible. Say again? We don't draw excited states because they only are instantaneous. The electron goes out and gets yanked back in as it drops back down. They don't get stuck in that outer state. Now, as that wavelength of light comes out, we can take a guess as to where it was with all that math we just kind of said we don't do. We can say, okay, the wavelength of light was from a 4-to-1 transition, ergo, it was probably out there at the 4th energy level. Yes? If you put the same quantity of energy in, it should get excited to the same value. But again, it's not going to stay there. It's going to like pulse in and out, in and out, in and out. Yeah. And you don't ever just do one atom either. You're going to have millions of argon atoms that you're exciting with electrons, and they're going to pulse in and out. Yep. All right. These are pretty pictures. So what is the magnetic spin with regard to an atom as the electrons move around? I was just reading an article the other day that electrons are not a sphere. They're actually, can't draw, kind of looks like a heart, doesn't it? That they're a little bit ovoid, that they have a center of negative charge, but they don't have a center of positive charge. They're a negative particle only, and as they move around, they have this, what we call spin associated with them. And it have two in the same place, they have to have opposite spin. That's called the Pauli exclusion principle. In this unit, you have to know the terms. You have to know the terms. You have to read through a question and go, okay, the common question is, which one of these is the Pauli exclusion principle being violated in? And you look through all of them, and you're like, okay, that's up, that's up, that's up, that's up, you know, and you find, oh, wait, you can't have two up in the same space. You're only allowed to have two valence electrons, or two electrons in an orbital, and they have to have opposite spin. The other thing is you can only have how many electrons inside an orbital? 2. Because if they have to have opposite spin, you can't have a third one because it would have the same spin as one of the other two. They always push each other right out of the orbital that's in. That's backed up by our findings scientifically. That's also backed up by the math that de Broglie and Einstein and them are all doing together. How many if each orbital can hold a maximum of 2 electrons, how many electrons can each of the following sublevels hold? I think we're pretty good, like S's can hold 2. How many can the 5p hold? 6. Now here's a trick question. How many electrons can a 5p orbital hold? An orbital can hold 2. An orbital can hold 2. The 5p sublevel is all of these orbitals. You see the slight annoying difference in the question? All right. So an orbital can only ever hold 2, but a sublevel can hold multiple because a sublevel is made of multiple orbitals. Which sublevel am I trying to draw here? 1, 2, 3, 4, 5, 6, 7. Yeah, that might be the 4f, or it might be the 5f, right? And this has 5 orbitals, so it might be the 3d or the 4d. Could be either one of those. All right. I found this diagram. I liked it a lot. It kind of shows you the energy distribution based off the different orbitals. As you split the sublevels, as you split the energy apart into sublevels, the 1 is the lowest energy level, and as you build up, we see a funny thing occur, don't we? See that the 3D actually requires more energy than the 4s, which is why they're out of order. The original math was just 1, 2, 3, 4, but through experimentation and much more complicated math, we realized the patterns were very different. Back to width. Why does it take more energy to remove an electron from aluminum plus 1 than it would from aluminum? Think about that for a second. Let everyone think. You're good and fast, I know, but let the other people think for a second. Aluminum plus 1 versus aluminum. Okay, now let's talk. What you got? The remaining electrons. Aluminum has 13 protons. This aluminum also has 13 protons. This one has 12 electrons because it's lost one. This one still has 13 electrons. So these remaining 12 electrons are going to get pulled in closer and be harder to remove. Does that make sense? Okay. Actually, we already kind of hit that the filling up is out of order. We have a lot of logic questions in this chapter similar to this one that we just went through, that if there's electrons missing, the remaining ones get harder and harder and harder to take. Mendeleev, he's the father of the periodic table. He and about 5 other guys were working on various forms of the periodic table at the same time. He had some sort of weird dream that he woke up from one day, and he says that he put down all 56 elements down like in one morning, except for 2. He had 2 backwards. And he had this weird dream that kind of inspired him. He'd been working on it for months. He skipped conventions. He skipped his job, trying to figure out what order to put things in. And one day it just kind of hits him. He uses a combination of mass and valence. But at the time, valence meant how things bond and react with each other. Now it means the number of valence electrons. But they correspond. He just doesn't know anything about it. And he realizes there's this repeating pattern that nowadays we call periodicity. The pattern repeats again and again. You go 1, 2, 3, 4, 5, 6, 7, 8. And then we get to the next period, 1, 2, 3, 4, 5, 6, 7, 8. And it keeps repeating, right? So he marked that down. He also noted that boiling points and densities followed a pattern within that pattern. Those are all facts about history. Are those things we ask about in AP Chemistry? No, they're just the interesting background stuff. Let's say that you had an element 116. Where would element 116 be on the periodic table? By the way, element 116 does exist now, but it's so radioactive that it's only for a fraction. What element is 116 under? It's under group 16. It's in the oxygen sulfur. So what would its oxidation state be? It would be a -2. So he looks at things like that. This element would land here. Here's what its properties would be. There are 4 elements. He predicts when those 4 elements are right, when are found, he's right in every respect. He is so sure of himself, he actually rebukes a guy who publishes bad data. There's a French scientist who finds germanium and publishes data that's wrong. And Mendeleev tells him he's wrong even though he hasn't ever seen it. And he tells him he's wrong in the journal. He writes back publicly in the journal. And the French scientist has to do more research, realizes he's wrong, and publishes a retraction and changes it. Which is why Mendeleev is then called like the king. Not really, but he's called the father of the periodic table. There's a couple mistakes in his periodic table, but they're not big ones. Things we already know. Electrons flow from lowest to highest if we're talking about ground state. Pauli exclusion principle holds. You can only have 2 electrons at a time. They have to have opposite spins. We know that how many electrons are held for each quantum number. What does he mean by that? He means S's can hold 2, P sublevel can hold 6, D's can hold 10, F's can hold 14. Hund's rule. I don't think we hit Hund's rule. A lot of people mess up Hund's rule. Hund's rule talks about degenerate orbitals, which sounds like you don't like these orbitals. These are the bad orbitals. No. What they're saying is that the electrons have to spread out before they can double up. They have to half fill all of the available space before you can have 2 within the space. So if you have, let's say, 2p4, 1, 2, 3, 4? No. That would violate Hund's rule. 1, 2, 3, 4? No, that would violate the Pauli exclusion principle. And knowing which violation, which thing you're violating, is required. I will put wrong answers out there, and you have to identify the wrong answer and identify why it's wrong. You got me? That's kind of weird, isn't it? Here we go. I'll do it right. This element probably takes what oxidation state and why? that was a tricky question. We don't really talk about it like that, do we? There's two ways to figure it out. Number one, you can go, what element is 2p4? Oh. I see people going, I see you can read Asha's lips. Oxygen! That's oxygen! It's oxygen. You go down, or use the femur. You're 1, 2 levels down in the P area. It's oxygen. That's oxygen. What's the oxidation state of oxygen? Why is it 2 minus? Because you can put 2 more in there to fill it up. Right? You can easily fill those last 2 spots to achieve a noble gas configuration. Wouldn't it have been nice if I'd put this up a second ago? Yeah, it would have been nice, but I didn't. Again, you need to be able... Oh, this was something that always gets me. When you look up... Ready to be irritated once again. When I teach you off-Bohr's order, that's the order in which they fill. That's not actually the distance they are from the nucleus, is it? Which might be the better way to write it? The distance from the nucleus or the order in which they fill? The distance from the nucleus is probably more important. So quite often, they get flipped around in final answers. Even though this is the order in which they fill, we will often flip the 4s to the last piece because it's the valence shell. So the last thing that's written down is the valence shell. Be prepared to see them written both ways. Good, Jacob? Oh, thank you for the staple. Do you got me by that? Your textbook, you didn't follow that? Your textbook will write it both ways. So if you're doing iron is argon 4s2 3d6. Which of these is really on the outside? 4s2. Yeah, I was wondering if I did that right. So for iron, they would actually write argon 3d6 4s2 because these are on the outside. That's the first line that gets attacked in bonding. They just switch them so that the last energy level is the last thing written down. The highest energy level, the farthest, or the valence shell. Iron usually takes a +2 charge. Where do you think those 2 electrons come from? I can't hear any. The last 2, yeah, this valence, there's those 2 right there. Why would those be the 2 that come off? They're on the farthest distance from the nucleus. Or it could be a +3. That's its other common charge. You've taken 2. What would happen if you took one of these? Be at 5, right? What would that look like in an orbital diagram? 1, 2, 3, 4, 5. The 6th one would fill that up, wouldn't it? And it takes one of the filled ones off. It takes from there, which is kind of weird. Actually, we already hit all this at the very beginning of class about noble gas configurations. Valence is the outside. The inside are called the core electrons, which seems to have a different implication this year than previous years. I used to call them the flex electrons. No, that's not true. Still, the core electrons mean the inside. The valence means the outside. All right, we're not doing periodic trends today. That's the future. Let's stop here. That was way too long as it was.